Welcome, everyone. My name is Amel Boulat, and for most of you, you know me. I'm the Industrial Liaison Officer for Alert, and welcome you to this series of webinars that will occur every other Wednesday. And Tiffany has been sending you emails. I'd like to introduce Professor Eric Miller and Dr. Dan Strellis. They are fine examples of what faculty industry collaboration can do for Alert and its community. And Eric has been working with Dan at Rapiscan for several years and with AS&E, a division of Rapiscan, for 8 years. And with that, please check out their links for their bios, and I'd like to hand it over to Eric.
Dan, I think so. Dan is going to start. Talk a little bit about the work, the nature of the collaboration. I'll talk some about the technical work we've been doing the last year and a half. Dan?
Yes, hello everybody. Thank you all for attending today's seminar, and it's been a real pleasure working with the Alert collaboration for many years now. And one of the collaborations that we've been working on for several years now is working with Eric's group at Tufts University. We kind of continued some work that was going on over with Aaron Couture's team at ES&E. And what we ended up doing was sponsoring through the Alert collaboration, a visit by a student. His name is James Weber, at the time, University of Manchester student that came over, visited Rapiscan and Tufts in summer 2017. We had at that time, through our industrial collaboration membership, we sponsored his research work. And so this collaboration, at least some of it that we'll be talking about today, has been essentially 3 years in the making. So it began back in summer 2017. This has been really fruitful for us. Working with academic partners is always a great opportunity for industry to kind of look at some basic problems through potentially some modeling and simulation that can be done to better define some challenges and problems that you may come up with in the future as you start developing new technologies. And we certainly have found this in this potential or this work that we've been doing with Eric's team. So this is basically motivated by some work that we're currently developing a small bore CT system that's framed on the notion of our stationary gantry approach as a company for doing CT imaging for security screening. So the project, we're calling it RTT6040. This is our small bore CT system development. What we'll be talking about today is essentially taking some theory about how we can best utilize the photons that are being put into the inspection tunnel to give us the maximum amount of information possible from any interactions that are happening in the tunnel itself. So what we'll be looking at here is a fusion of data streams, essentially, where we're utilizing X-ray attenuation data, Compton scatter data, and then also X-ray diffraction or Bragg scatter data, all in one system. And so it's a complicated and complex problem that really necessitates utilizing a thorough and rigorous modeling framework to start out with. And this is really where the Tufts team has excelled. And it's been a great work. And you can see there on the slide kind of a structure of our team. We have Ed Morton's an advocate of this technology. He was one of the first developers of stationary gantry CT system at CXR over in the UK, where Rapiscan acquired that company early on. We have our algorithm development team that's led up by Will Thompson out in the LA area. And there on the right, you'll see the team from Tufts, James Weber, Eric Miller, and Todd Quinto. So I think I'll just let it go to Eric now. I think he's gonna kind of take it over and start to talk about the system geometry and how they're utilizing the RTT geometry and the data being acquired from it to look at the modeling problem.
Thank you. So, yeah, so this is a problem that was posed to us, or sorry, a system that was posed to us by working with Ed and Dan like about 3 years ago. The very specific geometry of the RTT system is shown on this slide. So basically you have a little, can you see my pointer? Is my pointer evident? Do I need to?
Yes, it is. Yep.
It is. Okay. So you have a little object that's moving along here, and the folks at Rapiscan have sort of outfitted this tunnel with a bunch of sources and detectors. So they've put arrays of fan beam sources sort of around in one plane, a bunch of detectors more or less in the same plane, and those are used for attenuation imaging and some scatter imaging. And then out of that plane, out of the sort of as a function of Z, they've put these lines of other X-ray detectors, and all of these detectors are energy resolved. These will be used primarily for collecting Bragg diffraction data, so diffraction data as opposed to scatter. So the idea or the problem that we've been looking at was, okay, there are all of these different data streams. How can we make use of them to extract different information about the object or about a bag or a package that's moving along this belt? Okay, so let's start. So I wanted to spend some time discussing the more or less at a conceptual level, the different types of data that we collect. So attenuation, I think, is pretty well known to most of us on this call or people working in this area and doing any CT. You have a source that's emitting a fan beam. The attenuation data is basically collected by detectors that are located in some sense across from the source. And these detectors, so if I send out a bunch of photons, then as they make their way through the material sample, some of them leave the beam. They're either absorbed or they're scattered out of the beam. But what I measure here are fewer photons. So in that, I measured basically the attenuated photons. In that process, or that the physics associated with that, tell me something about the integrated, and we'll go into this in a little more detail, the integrated absorption, roughly the density of the object along that line. This is classic CT. This is more or less how, right? This is more or less how I would say 95% of people who play with X-rays deal with X-rays. But there are sort of the other 5%. Actually, it's not true. So there are the other 5% more recently who have been saying, okay, like I said, some of these X-rays scatter, and maybe we can measure the scatter. So the idea behind scatter tomography is that some of the X-rays come in, maybe they do scatter, they leave that beam, but they bounce off of something here, roughly speaking, and they move back, and you can measure the scattered photons at a receiver or a detector, like bounce back and forth with radar, at a detector not directly across. So if I measure so in addition to collecting attenuated photons by having essentially these green dots located above and maybe to the side, I get some idea of scatter. Scatter is a different beast altogether from attenuation. One of the interesting parts of scatter is that for the processes, the physical processes that are interesting to us, scatter changes energy, which makes the bookkeeping incredibly difficult. So the scatter process for electricity, for X-ray photons means that if I put in something at 1 keV, some of the energy in that 1 keV photon is going to be lost to the essentially absorption by it's going to mess around with the electrons in that atom. So what comes out is something slightly less than 1 keV. The process is Compton scatter. So there's a lot of interesting but also challenging aspects to looking at scatter. Also, there are a wicked few of them, right? So there are the signal to noise ratio, or the number of the Poisson rate for scatter is really low. So it takes a little while to get a bunch of them, enough to make sense of things. Okay, the third process that a bunch of people it's actually a classic process for analyzing crystalline materials and biomaterials is diffraction. So the diffraction setup for the RTT system, so Rapiscan system, is kind of challenging. It took me a little while to wrap my head around. So the way that it works, one way of thinking about it is I have this array of detectors located out of the plane where the fan is. These detectors are what I haven't shown here because my artistic skills are poor, is these detectors are collimated. So this red detector here corresponds to this red detector here. It's sort of focused to look only at this point in the fan beam plane. The little, I guess this is orange detector, it looks at this point. The yellow detector looks at this point. The green detector looks at this point. So if I start shooting photons into this fan plane, these detectors, this green detector, will only see diffraction that occurs at that angle. The yellow detector, similarly, the orange detector, and the red detector. So the way in X-ray diffraction, as my friends and colleagues from Duke know, one way of dealing with X-ray diffraction or enhancing X-ray diffraction is through there's been a lot of work at Duke in coated aperture imaging. Basically, this amounts to, again, to first order, roughly fancy apodization, right? So you got to know something about, you have to sort of focus these detectors in some way so that they know where their photons are coming from. Rapiscan has decided to solve this problem by essentially using, the word escapes my mind, but basically collimating these detectors so that they look at these little points. Another way of thinking about it, and the way that's turned out to be useful for us, is to rather than thinking about it as these lines going in Z, we think about it as arrays of detectors located in the X direction. And these arrays of detectors are all focused on a particular line in the fan beam plane. So what this array tells us is something about the diffraction of X-rays in this plane and along this line. So we get not line integrals, but line by line by line diffraction data. That's sort of the way this has all come together. Okay, so that's what we think of as the forward problem. The inverse problem, of course, is to say, okay, I give you the attenuation data, tell me something about the medium. Okay, again, a classic problem. There are, I think, probably, I can't see how many of you are online, but I'm guessing the vast majority of you know this problem probably better than I do. It's a classic problem of essentially recovering some information about the attenuation coefficient, the attenuation of this medium over line integrals. So the way the physics works out is I give you information about essentially the sum of the attenuation along this line. I give you lots of those sums from these sources, from other sources around. You tell me, you put the Humpty Dumpty problem that we have here is you tell me something about the attenuation in pixels along this line. Okay, this is an easy problem if you have all of the data around the object. For the fixed source geometry, this is less easy. So this is for the stationary gantry geometry that Rapiscan has built. It's less easy, but incredibly doable. And they've both in-house and with collaborators, Ed and Dan have like just an exquisite algorithms for solving this problem. Classic problem. Scatter is a little different and less obvious. So this is an area that's been of increasing interest, scatter tomography from X-rays, probably over the last 5 or 10 years. The literature goes back well into the 1990s. I think it's a paper by Steve Norton is one of the originals, who's another collaborator of the folks from Northeastern. We've known him for quite some time. So there are certain assumptions that need to be made because scatter is complicated. So we're going to assume single scatter, so only one bounce, which is reasonably good for the problems that we're looking at. We're going to assume that scatter is governed by the Compton process as opposed to Rayleigh or other. Again, a reasonably good approximation. We could talk about this offline. We're ignoring attenuation, which is a horrible approximation, but for the sake of getting there, getting somewhere on it, we're going to keep that approximation, knowing how to lift it. We do know a little bit about how to lift it. And for convenience, we're going to assume that rather than looking at the full problem of one detector, all sources, we're going to assume that scatter from each source is observed by one detector. Okay, and if we do this, so this source sends out data, this detector measures the data from that source. And if we do this, again, and all of these assumptions can be lifted. The last two are probably the most relevant. So if we do this, then it turns out that the scatter data are integrals. So again, sums of electron density over circles, pieces of circles, right? Again, not at all obvious. It's the fact that one gets this result. Again, it's well known, and it's intimately connected with the detailed mathematics and physics of this Compton scatter process. The radius of the circle is a function of the X-ray photon energy. So one of the beautiful things about the Rapiscan system is that it's energy resolving. Those are energy resolving detectors in that extra energy. So it becomes like a hyperspectral problem, but an X-ray domain rather than infrared domain. The beautiful thing, so a lot of this, the math is just absolutely beautiful. It falls out of the physics. The more energy we have, the better, the more circles we have, the better job we can do recovering, in this case, electron density. That's the physical property of the medium to which we are sensitive from observation of Compton photons. And like I said, of specific interest this year, sliding sources and detectors along the line. The last problem is Bragg diffraction. So again, this goes back, I mean, my Bragg diffraction, I think, was like week 2 of my freshman material science class in college, well known for like over 100 years. So the Bragg physics, again, are pretty easy to discuss. They talk about that it's usually used for imaging crystalline structures. It relates the energy of the photons or the wavelength to the atomic spacing of a particular set of planes and the angle at which they scatter. Okay, so for the interesting part that we found, at least for the RTT system, is sort of the structure of the problem that's induced by the geometry that Rapiscan has designed. So because we're looking at detectors, so I've kind of collapsed Z, because we're looking at linear arrays of detectors that are apodized or focused on one line, what we get is the fundamental sort of inverse problem that we're looking at from these data along one line is we're looking to image or get an idea of what's called the Bragg diffraction cross section. So F of Q in this case, you can think of as related to energy, almost, not quite, which is also makes for some challenges, as a function of space, as a function of X. So the inverse problem here is imaging this 2-dimensional quantity, F of Q and X, from energy resolved Bragg data along this line. This is a less well-studied problem. In fact, I'm not entirely sure that we're hoping that it wasn't studied at all, because if it was studied at all, we're going to have difficulties with the paper that's been submitted. But what we've done, or what I did, was lucky to do, was to meet James Weber, who is an awesome mathematician. He got it, like Ed said, or like Dan said, he got his PhD from the University of Manchester under the supervision of Bill Lionheart, who's one of the gods of this type of thing. And basically, I've been blessed for the last year. I say, James, here's the problem that we have. Come up with a solution. And the solution in this problem was less obvious, I would say, than the other problems. The scatter problem, or certainly the attenuation problem, it turns out that we can also represent the physics of the problem as integrals over lines. But these lines are now these very funny curves that are energy dependent. So this is a function of, think of this as a function of x and as a function of q, essentially. So, and this is way far from obvious, and is sort of at the boundary of my understanding. But we're given information about this thing that we're interested in, f of q and x, from integrals over these lines, these funny curves. Okay, and this was James's brilliance, was working this out. Okay, so the general overview here is that we have three data types. Attenuation, sorry, we have three data types: attenuation data, scatter data, Bragg data, that are all related to different properties of the material through integrals over curves. It's just the loveliness of X-ray tomography from a mathematical perspective. So here, I take very little credit. In fact, I take no credit. We brought in, James has been working with Todd Quinto. Todd Quinto is like one of the, we're lucky to have him at Tufts. He's one of the world's experts in this form of abstract tomography, to understand, to bring to bear some really hardcore mathematics, microlocal analysis, some differential geometry, about to understand what can we recover. So given the types of data that rather Rapiscan system acquires, what can we recover? Are we going to see artifacts? How stable is our ability to recover electron density or Bragg cross-section? If there are image artifacts, then the mathematics that James and Todd can do finds image artifact, can say very rigorously where there are image artifacts, what'll they be, what'll they look like? And then James has worked through this to actually, okay, given the nature of the artifacts, can we use this information to help design systems? In particular, how would we place sources and detectors to maybe minimize artifacts? So we've been looking at taking the very, very, very abstract mathematics and using it to begin to answer engineering questions, and also to begin to develop practical processing algorithms. So one of the nice things about these approximations that we've made is that they lend themselves to simple models that can be incorporated into real algorithms that are hopefully robust, or can be made robust to the approximations that we were making. So in the interest of time, I'll talk a little bit about this. So we've looked at two problems in particular. The first is the fusion of attenuation and scatter data from an RTT type of geometry. So again, the attenuation data is line integrals from sources to detectors. The scatter data are integrals over these circles from a source and detector that are moved back and forth. So this is sort of the abstract problem that we're looking at. We haven't looked at, right, this can be extended in all sorts of ways, right? We really would want to deal with more than one detector for scatter data. We'd like to take all of the data that goes all around the system. It can all, it could be done, and eventually will be done. One of the nice things about the mathematics is it can predict artifacts. So, and we know this from attenuation, that given that the nature of the sort of sources on top, detectors on the bottom, attenuation will do a good job resolving vertical edges and a really, really horrible job resolving horizontal edges. This is pretty well known. Less well known, but quantified very rigorously by James and Todd, is that given that nature of the scatter data actually provides really good resolution of horizontal edges and really poor resolution of vertical edges. So it's something we see in sort of simulation. It's something that's predicted analytically by the mathematics, the mathematicians.
Hey, Eric, this is Kristen. I just wanted to let you know 5 minutes left.
Okay. And okay, so we've been able to show that these are complementary data sets, and then we can basically use this information to develop techniques for imaging for fusing the data, attenuation and scatter data, for fusing them in a way that lets us do better than either one alone. So greater than the sum of the parts. And I'm pretty sure that Census will let you, or not Census, geez, Alert you can see the slide. So the details are the details. But what the bottom line is that the mathematics have led to a very implementable, like practically implementable algorithm that could be used to fuse data from scatter and attenuation. In terms of Bragg, the issue with Bragg is slightly different. It's a much different modality. Here we're interested in imaging crystalline structure. So the motivating application for the Bragg scatter, for the Bragg problem, was more CBP drug related. So can we find small quantities of some crystalline structure, aluminum, carbon, methamphetamine, of course, that's what's in bags or packages, embedded in paper or clutter. And here the types of images or the types of spectra, these Bragg diffraction spectra, they have a much different behavior. They're like spiky. They're very discontinuous. It's sort of what you would expect from the physics of Bragg diffraction. It's a challenging problem to recover the information, Bragg diffraction, from that limited data set. But I think the physics has helped quite a bit. James's approach, and we do a reasonably good job of recovering over a broad range of these Q variables, the spikes, the locations of these Bragg diffraction peaks for a variety of objects. We've also been of course, the problem is if you know the Bragg spectrum from different materials, can you use that spectral information to distinguish one material from another, narcotics from non-narcotics? Can you actually distinguish methamphetamine or some kind of drug from other kinds of drugs? We're a little less far along in this. I think we have reason to believe that there are things that certainly this is mislabeled, non-narcotics versus narcotics, easy to distinguish. Non-narcotic Bragg spectrum non-narcotics generally aren't crystalline, or at least a lot of them aren't crystalline. Easy to distinguish spectra that look from the blue from the spiky spectra that look like the red. Less easy to distinguish crystalline structures from one another. But even here, the narcotics, which are all the little red circles, tend to cluster with relatively few non-narcotic crystalline structures in the periphery. There's some hope then that diffraction data can be useful, and we believe that by adding in absorption data, which is of course the ultimate goal of something like the RTT, it provides absorption, scatter, diffraction. The objective is to combine those two for solving the real problem, which is materials characterization. Hopefully we can do that. Okay, so just to conclude on time, hopefully. So as Dan said, or to echo Dan's comments, we've had a wonderful collaboration under support with the folks from Rapiscan. They were responsible. Personally, I'm grateful for their finding James, putting me in touch with James, and the collaboration that sort of, and the opportunity to work with him for the last 2 years. Grateful for Alert for providing the support. We really, I'm a big fan of, despite the fact that I'm an academic, I'm a big fan of working with industry along these lines. I mean, at some point, we like to do abstract things in academia, but as an engineer, it's not sufficient just to publish papers. We want to have impact on systems. And I like to think that that Alert has provided me and a lot of us sort of professor types with the opportunity and actually the training to get this done, not just with Rapiscan, but with a lot of companies. So I want to thank you for your time. It was a great turnout, and if there are any questions, Dan and I are happy to do our best to answer them.
Yeah, thank you, Eric and Dan. There were a couple of comments in the chat area. One comment I wanted to address was that we will be putting this video up on our website. We are recording this at the moment, and it will be available for viewing on the website. Another comment that someone had made was that
So thank you for pointing me to Makovsky. Thank you, Fred. That I'll keep that in mind. And are we focusing on where the material density is considered uniform? No. we can image. So that's a harder question. The problems that we've been looking at, the problems that I showed at least, are piecewise constant density or piecewise constant material properties in general. The work that we've done is general enough to do material density as a function of space. It could change everywhere. It's a harder inverse problem given limited data. But we've certainly looked at that problem. It's again, I'll sound like an academic. In theory, it's doable. In practice, it requires some good head scratching.
There was another question. Someone asked, Carl asked, how is Compton scatter separated from other types of scatter?
By prayer is the answer. So the hope is that, at least in the case that we're looking at the backscatter data, the hope, and we've borne this out with like giant simulations, the hope is that most of the scattered photons you're looking at are associated with Compton scatter and single scatter. If we were to run like Giant or Monte Carlo simulations, that tends to be true. So, or that tends to be the case. In essence, then the non-Compton scattered photons that are in a particular energy bin in a particular detector get treated like noise. You could develop higher order scatter models. I doubt that it's particularly relevant for these types of applications. So yeah, it's crossing your fingers and hoping for the best and knowing a little in the physics, more or less bear it out.
So Eric, I have a question. Mike Solovich here.
Oh no, it's going to be hard, isn't it, Mike? Yeah. Michael?
Can you hear me? Can you hear me?
Yes.
Yeah.
I missed it. What's the question, Michael?
Yeah, well, the question was, you identified two major assumptions at the beginning that, needed to be incorporated in order to do the analysis. After the fact, have you been able to validate the impact of not lifting those assumptions?
Yes. So we have been, I'm not sure about the examples here, but when we take the math and develop the algorithms, we generally test them on data that are generated where those assumptions don't hold. So James has developed an in-house Monte Carlo code. So for example, in this case, we do account for attenuation due to paper clutter. So the data have attenuation effects in them. The attenuation effects aren't necessarily built into are not actually necessarily. They are not built into the inversion algorithm, so the processing. Essentially, we mop up those model-based discrepancies with regularization and with regularization techniques.
Mm-hmm. Very impressive.
How would you expand this knowledge to the high energy field? 6 to 9 MeV. I am not sure. I mean, I believe the physics aren't entirely the same. I think there are other ways X-rays at 6 to 9 MeV interact with material, pair production, things like that. We also don't deal with K edges or such. I would say that I would expand this knowledge to the high energy field by talking with you and figuring out what your problem is and then seeing how the ideas that we've used here could get mapped to it or adjusted.
Does anyone else have any other questions?
I have one more question that's sort of a general question. For people in industry that want to connect with Alert, Dan, from your standpoint, what was it that enabled you to reach out to Eric and develop, the nice collaboration that you have? How would you advise other people from industry to interact with us at Alert?
Yeah, that's a great question or point to bring up, Michael. I think, as you know, as an industrial entity, we need to focus our efforts sometimes on more product-focused things, and R&D sometimes gets a little bit put to the wayside. I would say. I would say that being in an R&D group has been fabulous, and we do put high priority into that, but there's only so many things you can do. So with that said, one option is to work on those academic collaborations. They're looking at things in a different way than you are, more of an applied engineering sense. And I think that one of the reasons we went to Eric's team originally was because of the great work they did with our collaborators at ASNE. That was one of the drivers there. So I find some good partners in academia, send them some funding to support your PhDs and postdocs, and I generally think you'll be rewarded.
So can I chime in on that, Michael?
Sure.
I mean, the other issue from my side of things is that DHS made this a priority, right? This was more than any other contract or research project that we've had. The sponsor said this is important, right, from the beginning, and they provided forums, these ADSA forums, for making it happen. I mean, what Michael and Carl and Laura have done with ADSA is, I mean, they told the academics, you got to get with industry, and then they said, here, twice a year, we're going to put you with industry, and that was like transformational. So a lot of credit to the government for making it happen. I mean, they provided the resources. And Alert really, I think, executed on that to make it easy for us academics, to meet folks that had interesting problems, like Dan. And in a couple of weeks, we'll talk with Pendar. Pendar, I met at when they were EOS I think it was Aspire or something. I remember running into meeting Mark Watinsky, right? And it's only because the sponsor made this, or it's not only, but largely because the sponsor made this a priority that we were able to accomplish this type of thing.
With that being said, Eric, that's very appreciated. I just want to alert people to the idea that the upcoming ADSA, which we hope will be given in November, will most likely be a virtual meeting. And the challenge will be to try and create that same kind of dialogue that Eric is referring to in terms of linking academia with industry. So for those on this call, just stay tuned. I don't know if Carl wants to make any comment about the upcoming event. Probably not.
I'm here. Yeah, we're talking to a number of people about how to do it, different processes to do it, but the big challenge is get this dialogue going in that forum. And we're looking at different ways, and in the short term, we're going to try running something, essentially a journal club or something equivalent to a very small group to start to experiment. And hopefully within a couple of weeks, we'll send out an announcement of what it'll look like. And if you have comments on how to do this, any ways to do this, please let me know. Just contact me directly.
Well, thank you, Dan and Eric, for this wonderful presentation. And thank you everyone for participating. I just wanted to let you know that we do have an upcoming webinar on July 8th with Professor Otto Gregory of University of Rhode Island and Dr. Brian Berlin of IT and Energy Systems. So if you haven't registered yet, you can send me an email. I will also be sending out an email after this webinar, so be on a lookout for that. Yeah, thank you everyone, and enjoy the rest of your day.
Thank you, Tiffany. You did a great job.
Thank you, Michael.
Thank you,
Thank you.
everyone, for joining.